Hi there, guys. So we're going to do 15C and 15D here, which is largely talking about adjacency matrices, and this is all for unweighted graphs in this case. Right, okay, so let's have a look directly at some of these examples. Now, first set of these examples is actually super simple. I think, I'm not going to spend a lot of time over this. It says just find the adjacency matrices for these two graphs shown. Now, these are the same. This is the same essentially as the adjacency tables that you've created before. It's just putting it in a matrix format. So, for example, in this case, you can see that you can create A, B, C, D down the side and A, B, C, D along the top. And so, if we were going to go from A to B, then we would need to put in a 1 in that case to say that that's possible to go from A to B. And likewise, it's possible here because it's not a directed graph. It's possible to go from B to A as well. So B to A is also possible. So we'll put a 1 in that position. Now, you can also have loops. That's coming up next. But here's obviously a directed graph. And in this case, you can see that you can go from D to C, but not from C to D. So D to C is possible. So we start on the left. We end up in the column. So D to C is possible, but C to D is not possible. From C, you can only go from A to A or to B. Okay, so that's pretty straightforward. Let's actually do these ones here. Let's hide that one up a little bit. Let's hide it behind there. And let's do this one here. And we're talking now about having loops as well. This, where they talk about a multi-graph, where there's multiple edges, as compared to a simple graph where there are no loops or multiple edges. I mean, you can see what a loop is, just going back to itself, basically, an edge which goes back to itself. I mean, multi-graph, you're not going to be tested on them saying it's a multi-graph or is this a multi-graph? Okay, so let's try and make it for A. Let's do this then. So let's come up with A, B, C, D. It's really horrible to write on this Active Studio program using the pen on this screen. A, B, C, and D, and then A, B, C, and D. So we can see that A doesn't go to itself, B doesn't go to itself, C doesn't go to itself, but D does go to itself. It goes to itself twice. You can go this way round or the other way round. So there's a 2 there in that case. A goes to B. Yes, that's possible, as B can go to A. A also goes to C. It goes to C twice, and it does not go to D. If you look at B, B goes to A, and it also goes to C. And if you look at C, C goes to A twice. Okay, and C goes to B as well, and C also goes to D, actually, so it goes 1 there. Now, actually, all of this on this side is just going to be copied onto the other side as well. So if you can do the line of symmetry, then that's useful. I might just, to make sure I've got it right, just check this one. So I've got D going to, D is going to A, no. D is going to B, no. D is going to C, yes. Okay, so there we go. That was just this column here transposed to the bottom left there. Okay, to a row. Okay. Now, obviously, this is fairly similar as well, so I'm not going to spend time doing that. But you can get some practice making some of these yourself. You can see the only difference here is that we've got directed lines. So although it's kind of similar, this one, we've got A to B, so A to B is allowed, but we do not have B to A. That is not allowed because there is no direction that's allowed in that way. Okay, so that's 15C. You can have a go at the exercise in that case. Now, there's an investigation before 15D, which you can have a go at, depending on the amount of time that you have available. Otherwise, you can go with this result. This result is pretty good. And it's talking about transition matrices. So it's saying that if you applied this twice, then you would get the number of routes that were possible So if you apply a multiplication of this matrix, if you do this matrix squared, then you will get the number of routes which are possible going between A to B, and so on, which have a walk length of 2. Okay, so that's just like using transition matrices when we're trying to find the ultimate probabilities of ending up in certain locations. Whereas in this case, we don't have probabilities, we just have number of ways to get to places. So when we do the multiplication here, we end up with the number of routes of a particular walk length. So, let's have a look at one of these questions. I mean, you can see the rule which is up here as well. It says here the number of walks of length r or less between any two vertices are given by the matrix SR, where SR is m plus m squared plus all the way up to mr. Now, that's actually walks of r or less. If you just want the walks of length r, you just need mr. So if you want all of the walks of up to that length, then you're going to need to add in all of the other matrices as well. So you'll need to add in the first matrix, which will tell you the length, all of the walks which are of length 1. The second matrix, which will tell you all of the walks of length 2 from, say, for example, A to B. And then all the way up to MR, which will tell you all of the walks of length r from A to B. Now, because they're always in the same position in the matrix, when you add those together, you will simply be adding that number of walks, say, for example, for A to B, that's the one of length 1, then you'll be adding the one of length 2 and so on, and they're always in the same position. When you're adding, you just add the same position to the same position, and so on. Okay, so let's have a look at one of these questions then. So this says, use these matrices to find the number of walks of length 3 between A and A, C and D in each of these cases. So let's try just the first one here. So let's just go to the calculator. I've got the TI and Inspire, of course. Got menu. We're going to go matrices. So 7. We're going to create a matrix here. Go matrix which is 4 by 4. So 4, tab across, and 4 again. Then OK. And we're going to put in the original matrix. So we've got 0, 1, 0, 1. And we've got 1, 0, 1, 1. And then we have 0, 1, 0, 1. And then finally, of course, we have 1, 1, 1, and 0. That's the final matrix. Okay, now because we want the number of walks of length 3, we're going to just say that to the power of, so I'm going to put a little power, so just the circumflex there. Where is it? Circumflex. There. Okay, so just our power key. You should know that, of course. And then to the power of 3. So I'm going to press OK on that one, and now I get this matrix. Why is that not showing up? There we go. We're getting this as the answer there. So 5, 2, 5, 2 to start off with. Okay, so that's telling us that from A to A we have 2 walks of length 3. We could list them if we wanted to as well. We could try and figure out what they were. But if we were going to figure out what they were, we would need to go back to the example of the graph. Okay, so you would need to really turn that into a graph. Now, these graphs come from 15C question 1, so let's just check that. So 15C question 1, we're saying that the graphs of length 3 from it was A to A was 2. So let's see, what could you do? You could do 1, 2, 3. Oh no, that doesn't work. Okay, let's try it out. 1, 2, 3. So there's one walk, and 1, 2, 3. There's another walk. In fact, of length 2, it's probably 2. 1, 2. Okay, so back and forth in that case. And of length 1, there's none. You can't go back to A with just traveling one path. That would just be a loop in that case. Okay, so you can actually find out from the graphs much easier than from the adjacency matrices the actual walks that are being performed. Okay, and from C to D, so from C to D, we can see in the matrix to the power of 3, we would be looking in this position here from C to D, we'd be looking at this position here. And for me, that's now saying 5. There are 5 walks of length 3. So let's just have a look at this. So just switch the color of that one. Okay, so from C to D of length 3, I guess we've got 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. Okay, so in that case, we should be able to find 5. Okay, right. So then let's have a look at question 2. It says, by considering an appropriate power of a matrix, verify your answer to exercise 15C, question 4, part C. So let's have a little look at that. Question 4, part C. Sorry, I didn't copy that one across there. So let's flick to that. So C, 4, part C there. So let's just focus in on this one. And let's pick that out. So it says, state whether there is anyone who does not know A's name and also does not know anyone who knows A's name. Okay, so they're talking about here this relationship here where there's people A to E, and we're saying, look, E here knows A and knows B and knows E. Okay, person I knows the name of person J. Okay, so person I is in row I. So person D knows the name of C, D, and E. But E doesn't know the name of person C. Okay, so this is the relationship that exists of knowledge that they are representing here. So when we go to look at the last part here, it says, state whether there is anyone who does not know A's name and also who does not know anyone who knows A's name. Okay, so anyone who does not know A's name is just C, D, and E. C, D, and E do not know A's name. And then you can also see that, and also who does not know anyone who knows A's name. Now, we can see that that's going to be, so C, I mean, from working this out, takes some time, we're basically looking for a walk of length 2. So not a walk of length 1. So a walk of length 2 would be saying, well, look, C knows B and B knows A. D knows C and C doesn't know A. D knows D. D doesn't know A. D knows E. E doesn't know A. So D and E both don't know A, and they also don't know anyone who knows A. Okay, so there's 2 people for which there are zeros there. So, but what they're requiring us to do in this case, okay, we're just going off on a bit of a piece on this one, but I remember this turned up in class, so that's why I'm kind of picking up on this one as well. So if we want to know the answer to that question, which is, again, let's have a look, state whether there is anyone who does not know A's name and also does not know anyone who knows A's name. What we're talking about there is actually, this gives us, this matrix to the power of 1 gives us all of the walks of length 1, but what we want is the walks of length 1 plus the walks of length 2, and that gives us what they're calling S2. Have I done that right? It's just, I think they call it S2 as in S2 like this. Let's have a little look. Okay, let's see. So yeah, they're calling SR in that case. S, they're just defining it as S. Okay, so what we need then is this matrix plus that matrix again to the power of 2. Now, I'm going to do that, in fact. I'm going to do the matrix. I'm going to create that. create this matrix. It's a 5 by 5 matrix. 5, tab across, and 5. I'm going to create this matrix here, and I'm going to put all those things in. I'm going to do 1, 1, 0, 0, 1. You can give this a go as well. 1, 1, 1, 0, 0. And then the next one is 0, 1, 1, 1, 1. Next one is 0, 0, 1, 1, 1. And finally, we're getting 0, 0, 0, 1, 1. Now, I'm going to say that that is matrix A. So I'm going to store that. Control and variable allows me to store it as matrix A. So what I'm going to do now is say, I'm going to do A plus A squared. And that gives me, whoop, well, for some reason it's not picking it up at the moment. That gives me this, there we go. It gives me this matrix here. Okay, so now in the first column there, you can see that C to A, sorry, D to A and E to A both have a 0 in them. That's in the first column. That's, where are we? That's here, whoop, that's here and here. Those two zeros there indicate that there are no walks of length 1 or walks of length 2. Okay, so that's what they're talking about in that question there. Okay, well, I've thoroughly spoiled your practice in that case, but I know that turns up as a question in the class, and that was kind of an interesting question. Okay, so that's it for C and D. I think the internet's just stopped there on that one, so it's probably about time to stop there. Coming up after this, we're talking about more transition matrices here. So we're going to use transition matrices further in this case. Okay, so that's going to turn up in 15F. Okay, thanks for listening.